welcome. The topic we'll be discussing in this lecture is actually we'll be moving to a fresh chapter which is IO input output module. Okay. So with what we have discussed last class, with that we have finished discussing about a memory subsystem, right? So now we are moving to the next chapter which is IO subsystem. So in IO subsystem, basically we are going to discuss about three types of IO operation. Okay, one is programmed IO. We are going to discuss three types of IO operation. These are programmed IO, interrupt driven IO, and DMA, direct memory access. Okay, this is the core or essence of this particular chapter. So first, let us try to understand what is an IO module. What is meant by IO module? Okay. See, apart from CPU and memory module, another important module in a computer is the IO module. So what is IO module? IO module is a separate module, or it is a separate what you call it is a separate, you can call it as a processor or a controller which connects several IO devices. That is, IO devices are connected through the IO module. Okay, and also IO module is connected with the system bus. What is system bus? System bus include these things: address lines, data lines, and control lines. Okay, using system bus only processor and memory can be accessed. Okay, I mean CPU, the interface with the CPU and memory also happens only through the system bus. Okay, so one end of the memory module, IO module, so this system bus is connected with CPU and also it is connected with memory module. Okay, so yeah, so the system bus is connected with CPU and memory module. So if some communication between memory and IO should happen, also that should also happen through system bus. If any communication between CPU and IO happens, also that should also happen through system bus. Okay, so one end of the system IO module is connected with the system bus, and another end of the IO module is connected with the various IO devices. Okay, so you can say that IO module acts as an interface. IO module acts as an interface between the processor and the IO devices. Okay, so it means that the processor is not going to communicate with the IO device directly. Okay, so all these are IO devices. We'll call it as device 1, device 2, device 3, so on and so forth. Okay, so processor is not going to communicate with these IO devices directly, rather it is going to communicate through the IO module, right? Now you may ask, why is it so? Why not the processor can communicate with the IO device directly? Why not it can communicate directly? What is the need for an IO module in between? Okay, the reason for that is there are diverse type of IO modules. Like different IO modules works in a different style or in a different method. Okay, so it is not that all IO module work in a same method, right? I mean the way in which the IO devices works very diversely. Okay, so all these diverse features cannot be incorporated into the CPU. All these diverse feature, it is impractical to incorporate all these features into the CPU, right? Hence hence we need a separate module which will take care of this. That is one of the reason. Hence we need a separate IO module which will take which will which will so which will ensure that CPU need not bother about the diversity of the IO devices. Okay, CPU will just say that I want to read from so and so device, or I want to write to so and so device, but the uh, but the but the way in which something to be read from one particular device and the way in which something to be read from another device may not be same. They may be entirely different. So these details IO module will take care. These details, in CPU need not bother about these details, right? So that is one of the core reason why we need an IO module, right? And another reason is there is a huge speed mismatch between processor and the IO devices. Generally, processor will be very fast and IO device will be very slow. So it is impractical for the processor to directly communicate with with IO devices because there is a huge speed mismatch, right? So to to ensure that this speed mismatch is mapped properly, for that also we need an IO module. Okay. So IO module, what it will do, it will maintain some buffer. It will maintain some buffer. So if, for example, if CPU want to send some data to a particular IO device, this particular device 1, then CPU will send at a very faster rate, right? But IO device cannot receive the data at that fast rate. Okay. So but now the data will be sent only through the IO module. So IO module will collect the data and it will keep it in the buffer. Okay, IO module will collect the data at the rate at what speed the processor is spending, at that sending, at that speed it will collect and it will keep it in the buffer. Then according to the device speed it will slowly send to the device, right? So this is also one of the reason why we need a separate IO module. Okay, so generally IO device will be very slower and CPU will be very fast. Okay, but at some rare cases IO module, the speed of the IO module may be higher than the speed of the CPU, right? It's very rare scenario, but it may happen. It may happen that sometimes the speed of the IO device may be higher than the speed of the CPU, right? So in that case also there is a speed mismatch. Anyway, there is a speed mismatch. Now the CPU is slow and IO device is fast. Okay. Now if something is to be transferred from the IO device to the CPU, and if there is no IO module, this device will transfer data at a faster rate and CPU may not be able to receive at that rate. Then also you need an IO module to buffer, right? So these are the different reasons like why we need an IO module, right? So IO module is a separate block, or it is the interface through which the CPU communicates with the IO device, right? Okay. So how IO module communicates with the CPU means through the system bus. And what is system bus? System bus is the combination of all these three things: address lines, data lines, and control lines, or you can call it as address bus, data bus, and control bus. Okay. And through each IO module several IO devices can be interconnected, right? So it is not that your system will have only one IO module. The system may have several IO module. It depends. Okay. The system may have several IO module. Okay. So this is the introduction to IO module. Fine. See, external devices in the sense any IO device. External means something which is not a part of the computer. All IO devices are what? External devices. You take keyboard, mouse, printer. Are they inside the computer or outside the computer? It is outside. So all these are external devices. Okay. So IO module acts as the interface. Another way we can define IO module something like this. It acts as an interface between the external device and the internal device. What is the internal device? CPU is the internal device. Main memory is the internal device. All these are internal devices. These are connected through the system bus. Okay. So this IO module is the one which acts as an interface between the external device and the internal devices. Okay. Fine. Right. So this slide is generally, it is very what do you call, very preliminary. It is talking about IO devices. What are the different IO devices? Keyboard, mouse, all these are the IO devices, right? So I'll skip this. Okay. Now let us see what are the functions of IO module. What are the core functions of IO module? So IO module has mainly these functions. These five functions. What are they? To control and timing. Control and timing, processor communication, device communication. Here device means IO device. Okay, device means whenever we say device, it refers to IO device. Data buffering, error detection. These five are the core functions of the IO module. Okay. Now what is control and timing? Control and timing means it coordinates the flow of traffic between the internal devices and the external devices. Okay. Or we can call it the internal resources. Devices means it always refers to the external device. Okay. Internal resources means CPU, and mainly we are talking about CPU and memory. Okay, CPU and memory are the two internal resources we are talking, right? And what is external device? External device means any IO device, any IO device. Now, IO module is the one which controls the which coordinates the flow of traffic, between the internal resource and the external devices. So coordinating the flow of traffic means what? Again it's the same thing. For example, the IO device may be very slow, right? In that case, if CPU wants to send something to the IO device, then the CPU will send very fastly. Okay, now this speed should be coordinated. Who will do this coordination? IO module will do the coordination, right? Okay. Or sometimes IO module may want to send something to the CPU. Say this IO is a keyboard. User is typing something, it should go to the keyboard. But keyboard is a very slower device. It will send data at a very slower rate. But CPU is a very faster device. It wants data at a faster rate. Now somebody should coordinate this. This coordination will be done by IO module. Okay. Here coordinating means what? So coordinating means if data is coming from the keyboard, if one character comes, immediately IO module will not send it to the CPU. Rather, it will keep it in the buffer. It will wait for 10 characters or 20 characters or 100 characters to come. Once that many characters came, then it will send to the CPU. Because CPU want data at a faster rate, right? Similarly, when the data is flowing from CPU to IO, it will keep in the buffer. CPU is sending fastly, it will keep it in the buffer. But the IO device cannot receive it at that rate. IO device may be able to receive in a very slower rate. So according to the rate of the IO device, it will send the data at that speed, right? So that is called as control and timing. Okay. So it basically coordinates the flow of traffic between the internal resource and the external devices, right? Okay. And then the IO module also perform communication with the processor. Okay, because IO module acts as an interface between the internal resource and the external devices. So it also performs the processor communication. Okay, processor may give some command like I want this data from so and so IO device. So it will give a command. Okay, that command should be decoded first. That command should be decoded so that the IO device will understand what to be done. Then it will perform that particular operation on that particular device and it will give the result. Okay. Then data status. See, it is not that all operation will be successful. Some operation may be successful, some operation may not be successful. So CPU is giving a command, read the data from so and so IO device. Okay. So the IO module will read from that IO device. Okay. So after reading, what is the status? Whether the read is successful or not, or is there any error happened? So that is called a status reporting. Okay. The next is address recognition. Address recognition means what? See, even the IO device also have address. Okay. So every IO device should be identified uniquely, right? Say for example, in the system we have keyboard, mouse, printer, all these things. Then there will be an address. There will be an address for keyboard. Okay. Like how in memory each location we have address. Similarly, every IO device also will have a unique address. For keyboard there will be a unique address. For mouse there will be a unique address. For printer there will be a unique address. I mean, whatever the IO device that you are using, for every IO device there will be a unique address. Okay, right? Now if CPU want to print something on the printer, CPU will not say that print this data on the printer. No, CPU will send some data and it will send the address of the printer. If the printer's address is 15001, say this is the address which is used to refer the printer. So this address means it is printer. Okay. So 15001 is the identification or the address of the printer. So CPU will say that print this data to 15001. Now what is 15001? 15001 is the printer. Okay. So there are many devices connected to the IO module. So it is the job of the IO module to recognize the address. CPU, because processor will send everything in terms of address. So processor should which address, or this address refers to which device, that the IO module should be able to locate. Okay, so that is called as address recognition, right? So this is about processor communication. That is, whatever processor is communicating, the IO module should be able to decode, and it should be able to perform the appropriate action, and it should report the status to the processor again, and also it should be able to recognize the addresses. So every IO device will be uniquely identified by an address. Okay. So IO device, like how it is able, it should be able to communicate with the processor. Similarly, it should be also able to communicate with the device. What is device? IO device. So because it is acting as an interface between the processor and the IO device, so it should be able to communicate with any of the IO device by giving some commands, okay, or by reading the status information of that particular device, whether the device is ready for communication currently, or already the device is busy with some other task. Like that, it should be able to communicate with that particular device. Okay, right? It may also give command to the device, do this, read this data and give it to me, like that. Okay, fine. And next is data buffering, which we have already discussed in control and timing also. That is to normally there will be a speed mismatch between different devices like processor and memory, sorry, processor and IO devices. So there will be some buffer in the sense some temporary storage will be available in the IO module. Okay, so whatever CPU sends at a faster rate, that will be kept in the buffer before it is being transferred to the IO device. Later it will be transferred to the IO device at a reasonable rate which is acceptable by the IO device. Okay, similarly, when the data is transferred from IO device to the processor, again the same thing will happen. IO device will send the data slowly, so it will be loaded in the buffer. Once sufficient amount of data came, then it will be sent to the processor at a faster rate. Okay. Apart from this, IO modules also should be able to perform error detection. Okay, because all operation we cannot say that it will be going on properly. So in between, if there is any error happen, the IO module should be able to detect, using various error detecting schemes like parity error checking or whatever it may be. Okay, fine. So this is the structure of an IO module. So this is the block diagram of an IO module. So IO module contains what? It contains data registers. So these data registers are otherwise called as buffers. These are registers. Okay, like how in CPU we have registers. So the registers are nothing but some temporary storage area, right? So similarly in the IO module there are the registers, data registers. So these registers are otherwise called as buffer. These registers are otherwise called as buffers. Okay, so here only the IO module will store, if for example if processor is sending data at a faster rate, in these registers only it will store. Okay, and then later it will send to the IO device at a slower rate. So we have data registers inside the IO module. Similarly, we have status or control registers. Okay, which says the status and control, which is used to which gives the status of different IO devices, whether a particular device is ready or not, or what, like that. Okay, or is there is any error or not, right? So this particular register is used for both status and control. Status in the sense which says the status of a particular IO device, whether that IO device is ready for communication, or is it busy with something else, or is it currently not working, all those things. Control means it is used to give some command, perform read operation, read from that device or write into that device. So that is called as control. Okay. So these data registers and status registers are directly connected with the data lines of the system bus. Data lines of the system bus. So it means that from system bus, if processor want to write some, say that processor want to print something, on the printer. Okay. Now where the processor will send that data, it want to print something. So that data it will keep in the data bus, right? It will keep in the data bus, right? This is data bus. And from data bus, that data will go into where? This data registers. Okay. So now the data to be printed has come to the data registers. Okay. Now the control register will give the appropriate control signal for that to be printed. Then it will be printed, right? Okay. So this is for sending data from CPU to data register. Okay, if something to be printed, then it should first come into the data register of the IO module. Without that, it cannot be printed. Similarly, you take the reverse case. For example, if some device is sending data to the CPU, say keyboard is sending data to the CPU. So user is typing something and that should go to the application program, okay, via CPU, right? So now first where it will come? It will come to the data register, because keyboard is a slower device. So maybe the user may be typing characters. So first 10 characters will be stored here, right? First, and then all these 10 characters will be once a set of characters comes, it may be 10 or 50 or 100, whatever it may be, then it will be placed in the data bus. Okay, once it is placed in the data bus, it will be available for the processor, right? So this is how data is transferred from the processor to the IO device, or from the IO device to the processor. Okay, fine. And here we have an IO logic. Okay, so which is used to give commands like read from the device or write from the device, all these things. See, the control registers will generate the signal, but that signal will be performed through the IO logic. Okay, and again this IO logic is also connected to address lines, and also it is connected with control lines. Okay, it is connected with address lines, and also it is connected with control lines. What is address lines? Address lines are used to uniquely identify a particular device. Okay, say for example we have three devices. Simplicity sake, say the address 00001, it refers to keyboard. I'll just call it as K. Okay, the address 00010, it refers to mouse. Okay, the address 00011, it refers to printer. Okay, now we have three devices were identified by these addresses. Okay, say for example, now CPU want to perform a read operation from the keyboard. From keyboard it can only read, you cannot write anything to the keyboard, right? So then which address should be placed here? The address should be 0001, that address will be placed. Okay, and the control register will generate a read signal. Okay, which means that data should be read from this address. What is this address? 401, it refers to which device? It refers to keyboard. Are you getting? Okay, right? Say for example, the CPU want to print something to the printer, then instead of this address it will keep this address 00011. So in this address something to be done. What is this address? Printer. And what operations to be done? Now I want to perform a write operation. So what is to be written? Whatever in the data register, that is to be written. Okay, so this is so the IO logic is used to, using IO logic only, the processor, the IO module is going to uniquely identify that particular IO device with the help of this address. Okay, right. And now you can see here there are different device interface logic. Device interface logic 1, device interface logic 2, 3, like that. There are many external device interface logic. Okay, so through each of this logic, each IO device will be connected. Okay, through each of this logic, one IO device will be connected, right? So say in our case, if we assume there are three IO devices, then three of this logic will be used. Okay, to one of the interface logic, one IO device will be connected. To another interface logic, another IO device will be connected, and to another one, another IO device will be connected. Okay, so here we will have an IO device. Similarly, here we will have an IO device. Okay, again there are three status lines between the IO device and this device logic, external device interface logic. What are they? Data, status, and control. Data is used for transferring data to that particular IO device, or to receive data from the IO device. Status is to know the status of that device, whether the device is ready for communication, or is it busy or what. Control is used to send control signal, like what operation should be performed on the device, whether you want to perform a read operation or write operation. Okay, these two are the commonly used control signals. Okay, right. So this is the general block diagram of an IO module. Now there are three techniques possible for IO operation. What are they? They are programmed IO, interrupt driven IO, and direct memory access. Okay. So in this lecture we will try to focus on programmed IO, right? In this lecture we will be focusing on programmed IO. So basically there are three techniques are possible for IO operations. These are programmed IO, interrupt driven IO, and DMA, right? For in programmed IO and interrupt driven IO, the for performing the IO operation, the involvement of the processor is required. Okay. For programmed IO and interrupt driven IO, to perform the IO operation, the involvement of the processor is required, very much required. Without processor, this programmed IO and interrupt driven IO cannot be done. Okay. But that is not the case for DMA. For direct memory access, processor's involvement is not required. Okay, right. So let us try to understand what is this. So with programmed IO, what happened in the sense, data can be exchanged between the processor and the IO module. Okay, processor executes a program that gives a direct control of the IO operation. That is, processor, it is as if processor is performing IO operation directly. Okay, when the processor issues a command in the sense command to perform an IO operation, that is to read from an IO device or to write to an IO device, then the processor must wait until the IO operation is completed. This is one of the drawback of this scheme. Okay, that is the so this scheme is used to exchange data between processor and IO module. That is, you can send data from processor to IO module or from IO module to processor. Okay. So, but the drawback is, if the processor gives a command to perform an IO operation, then until that IO operation is completed, the processor should wait. The processor should wait until that IO operation is completed. Okay. So, if the processor is faster than IO module, normally the processor will be faster than the IO module. Generally, processor will be faster than the IO module. Then what will happen? This is a wasteful of processor time. Okay. So this is how, but this is how the programmed IO works. Okay. So through program instructions, it can directly access the respective IO device, right? Of course, through the IO module only, but and it can give the command to perform the IO operation. But until then IO operation completed, it should wait. So there is a waste of time here. Okay. But coming to interrupt driven IO, here the processor will just issue a command to the IO module stating that I want to read the data from so and so IO device, or I want to write the data to so and so IO device. Like that, it will just give a command. After giving the command, the processor will continue to execute other instructions, or if it has some other job to do or some other process to execute, it will start doing that. It won't wait for this IO to complete. Processor will just issue a command to perform that IO operation to the IO module. Okay, then immediately it will start doing its other job. Okay, once this IO operation is completed, processor has given an instruction for the IO module to complete to do an task, right? Once this IO operation is completed, the IO module will generate an interrupt. Okay, once the IO operation is completed, the IO module will generate an interrupt to the processor. Okay, now the processor will understand, okay, the job is completed. If the processor is asked to read some data, then it means that the data is available in the buffer of the IO module. Then it means the data is available in the buffer of the IO module. Okay, now it can request from IO module to transfer that data. So then the IO module will place the data in the data bus and processor can take the data. This is case of read. If it is a write operation, then it means processor has written some data to the buffer and it has asked you to write it on some IO device. Okay, then if the processor, after sometimes if IO module generates an interrupt and says that the operation is completed, then the processor will just understand that, okay, the data has reached the destination IO device. Okay, so the difference between the two is, in programmed IO and interrupt driven IO, is in programmed IO the processor will give the command and it will wait until the IO is completed. Whereas in interrupt driven IO, it is not required for the processor to wait. It will just give a command and then it will start doing its other job. Okay, and once the IO operation is completed, the IO module will generate an interrupt to the processor. Okay, and then the processor will do whatever it is supposed to do. Right? Okay, so this is how programmed IO works, and this is how interrupt driven IO works, and both of them, they actually the involvement of processor is required. Okay, whereas for the third method, using direct memory access technique, processor involvement is not required. For direct memory access method of uh, transferring data between memory and IO module, okay, between memory and IO module. So normally data is transferred from where? Even though we say processor, it is a processor to IO or IO to processor. Actually, it is transferred from memory to IO. Okay, so anywhere you see, if you are transferring data from, it is transferred from memory to IO module and then IO to memory. Okay, from memory the processor may fetch. Okay, but in case of programmed IO and interrupt driven IO, processor should involve in that. Whereas in DMA, processor involvement is not required. Data can be directly transferred between memory and any IO device. Okay, so we'll be discussing in detail about DMA later. Fine. Okay, so these are the three ways of whatever we have discussed. This table actually summarizes this, right? Three methods of IO techniques: programmed IO, interrupt driven IO, and direct memory access. So, so, so transfer of data between IO to memory through processor, either IO to memory or memory to IO through processor. If through processor, for both this technique, processor is involved for programmed IO and interrupt driven IO. Programmed IO does not use any interrupts. That is, processor will give a command and it has to wait until the IO is done, right? Whereas interrupt driven IO will give a command and it will start doing other jobs. Once this particular IO is completed, the IO module will generate an interrupt. So it uses interrupt. Okay. So interrupt driven IO uses interrupt, programmed IO does not use interrupt. So directly transferring data between IO to memory or to memory to IO without the involvement of processor, that technique is called as DMA. Right? These two techniques needs the involvement of processor to transfer data between memory to IO or between IO to from memory to IO or from IO to memory, right? Okay. So there are four types of command that an IO module may receive from the processor, or we can say that the processor may issue four types of command to the IO modules. What are they? Control command, test command, read command, and write command. Okay. So control command is to activate a peripheral and to inform that like what to do. Control means it's a control operation, whether you want to perform a read operation or a write operation, like that. Okay, it is to activate a peripheral. Peripheral means IO device, and to issue a command like what operation it's supposed to do. Okay. Right. Test command is used to test the various status conditions with an IO module and its peripherals, because each IO module is connected with several peripherals, right? So it is used to test the status condition of an IO module and the connected peripherals. Okay, whether a particular peripheral is ready for communication or not, or is it busy. Such commands are called as test command. Okay. So read, it is used to read something from an IO device. Okay. So it causes the IO module to obtain an item of data from the peripheral and place it in the internal buffer. Okay. So the read command, what it will do, once the read command is issued by the processor, the IO module will fetch the data from the particular IO device. So and so IO device you want to read. So if it is keyboard, the IO device will fetch the data from that particular IO device and it will keep it in the buffer, internal buffer of the IO module. Okay, this is IO module. I'll call it as IOM if this is IO module, and if this is the buffer, then the read command, what it will do, it will fetch the data from that appropriate module and it will keep it in the IO buffer. Okay, right? Write command will do the reverse. the IO module will write the content of the buffer to the respective IO device. If it is some other IO device, it will write. Okay. It causes the IO module to take an item of data from the data bus and subsequently transmit the data to the peripheral. Okay. So how the data is coming to the buffer? It is coming from the data bus. Okay. So either we can say it is directly taking from the data bus and writing to the IO device, or this is data bus. Okay. It is directly taking the data from the data bus and writing to the IO device, or from data bus it comes to the buffer and from buffer it goes to IO device. Either way. Okay. So basically the IO module take and data from the data bus, okay, or from the buffer and transmit the data item to the respective peripheral. So these are the 4 types of commands issued by the processor to the IO module. Okay. So this particular flow chart actually it explains how the different IO techniques work. The first is a programmed IO, next is interrupt driven IO, the third is DMA. Okay. So we will refer this slide later also. As of now, let us focus only on the first diagram. Let us not focus on the remaining 2 flow charts. Okay. Let us see how the programmed IO works, because first we are going to talk only about programmed IO. Our major concentration is on programmed IO. Of course 3 types of IO is there, but now we will be discussing in detail about programmed IO. Okay. So how it works in the sense, initially CPU is giving a command to the IO module. So CPU to IO, what is the command? It is issuing a read command to the IO module. So this is used to, this flowchart is actually used to perform a read operation from the IO device. Okay. CPU is giving a read command to the IO module. Okay. Then the IO module, what it does in the sense, then the status of the IO module, then the status of the IO module is checked. Okay. Then the status of the IO module is checked. Okay. If status means what, here status means what, actually processor is checking the status. Processor is given the command. Okay. You recall in the programmed IO, after giving the command, what the processor should do? Processor should keep on wait. Processor should keep on wait until the operation is completed. Okay. So after issuing the command, processor is keep on checking the status of the IO module. What it is checking? Whether that read operation is completed or not, whether it is completed or not, whether it is completed or not, like that it is keep on checking. Okay. Check the status, again do this, check the status, again do this. So it means that processor is waiting. So this loop says that processor is waiting. That is what it means. Okay. After issuing the command, processor is reading the status of the IO module and it checking the status, that is it ready or not ready. Ready means the data is ready or not. Whatever the data I requested, is it ready in the buffer or not. As long as it is not ready, processor is not going to do anything else. It is going to keep on wait. It is going to repeatedly do this, right? Once it is ready, then the processor know that by reading the IO, CPU knows that okay, the data is ready. Then control comes here, ready. If it is ready, if the data is ready, control comes here. Then read the word from the IO module. That data is available in the buffer, right? So read that from the IO module and write it to the memory. Okay. That is, here we want to read data from the IO and write it to the memory, right? Previously I was saying CPU, but actually CPU means what? CPU it don't directly go to the CPU, right? It first go to the memory, right? Okay, fine. So this is how programmed IO works. Okay. So what it does, it gives an IO command and then it checks the status of the IO module. It checks whether it is ready or not. As long as it is not ready, it keeps waiting. Okay. If it is ready, the data will be available in the buffer. Then read the data from the buffer and write it to the memory. Okay. If it is done, yes, then go to the next instruction. If it is not done, then again issue the read command. Okay. So this is a brief overview, like how the programmed IO is working, right? Okay. Again, with programmed IO, as we have already discussed, Each IO device connected through the IO module is given a unique identifier or address. Each IO device connected through the IO module is given a unique identifier or address. Okay. This this addressing of IO device is actually of two types. This addressing of IO device is actually of two types. One is called memory mapped IO. One is called memory mapped IO, and the other one is called as isolated IO. Right? So the point here we are discussing is each of the IO device will be given an IO will be given an address. Okay, and this addressing scheme, this how this address is allocated in this this address was given based on two techniques, two models. Either it can be a memory mapped IO or it can be isolated IO. So what is meant by memory mapped IO? Memory mapped IO in the sense, assume that your system has 10 address lines. Assume that your system has 10 address lines. Okay. So using 10 address lines, how many locations can be addressed? 2 to the power 10 locations. Okay. Using 10 address lines, we can address 2 to the power 10 locations. What is 2 to the power 10? What is 2 to the power 10? It is 1024. 2 to the power 10 is 1024 locations we can address. Okay. Right. Now, for example, I may not use all these 1024. Now, I may not be using all these 1024 locations for my memory, right? Say my memory is very less. Say my system memory is only 512 MB. Okay, my system memory is only 512 MB, right? Now I don't want all these address bus. Okay, I need only 512 lines. So using 10 lines, we can address 2 to the power 10 locations, that is 1024 locations. Now my memory is only 512 MB, so I need only 500 512 MB memory locations only I have. Okay, so out of this 1024, I need only 512 combinations to access the memory, right? Then remaining 512, what can I use? Remaining 512 combinations of zeros and ones of this 10 bit, okay, can be used to address the IO device. Can be used to address the IO device. Okay, so this is called as memory mapped IO. This is called as memory mapped IO. Because why we call it as memory mapped IO? Basically, these address lines are used for what? Basically, this 10 lines you are provided. The system is providing you 10 lines. These 10 lines are used to address the memory. It is not provided for the sake of addressing IO device. It is only provided to address memory. Okay, but actually you don't need 10 lines. I need very much lesser than 10 lines. It is, for me, it is just enough to have 512 locations. So I don't need 12 lines. Oh, I mean 10 lines. Okay, so then what can I do? I can use the remaining bits. I can use the remaining bits for what? For addressing the memory. Sorry, for addressing the IO. The remaining bits I can use to address the IO devices. Okay, so this is the whole concept, right? So that means the address lines were shared. It means the address lines were shared between memory and IO devices. So that is called as memory mapped IO. The system is having only one set of address lines, but that set of address lines itself is shared between memory and IO devices. Okay, so that concept is called as memory mapped IO. Devices and memory share the same address space. Okay, IO looks just like memory read or write. Okay, processor cannot differentiate. In this case, processor cannot differentiate which is a memory read operation, which is IO read operation. Processor does not know, because we are using the same address bus. Okay, in that some of the address will refer to memory, some of the address will refer to the IO device. Okay, so processor will not be able to differentiate whether it is a memory read operation, write operation, or IO read operation, or write operation. Okay, and also there will not be any special commands for IO operation. Okay, whatever the commands available for memory operation, the same command should be used for IO operation, right? For example, for reading from a memory, If you are using the signal R, then the same R will be used for reading from an IO device also. If you are using the signal W to write to an memory, then the same signal will be used for writing to an IO device also, right? There is no way to differentiate whether some address is referring to a memory or some address is referring to an IO device. Okay, only with the address, the only the address is the identification. This address is memory, this address is uh, IO device, nothing else. Okay, right? Fine. So that kind of, what you call, that kind of mapping IO device is called as memory mapped IO, right? Fine. Okay, right? So okay, then the second type is isolated IO. Isolated IO means what? Isolated IO means you'll have two different address bus. There will be a dedicated bus to address IO device. See, you have a separate bus. There will be a separate 10 lines. There will be a separate 10 lines to address memory, using which you can address 2 to the power 10 locations. Similarly, there may be a separate 7 lines to address IO devices, using which you can address 2 to the power 7 IO device. Okay. Now we are not sharing one bus. Please mind, this is the difference. Now we are not sharing one bus. There is two separate bus. This is one separate bus. This is a separate bus. Okay. For IO now we have a separate bus. If you have a separate bus or address lines for IO device, that is called as isolated IO. There will be a separate address space. Okay. So IO and memory lines will be different. So now the processor can differentiate like which is IO lines and which is memory lines. And for IO lines there may be special commands. The command for memory will be different and the command for IO will be different. I mean the slightly there will be a different. For example, for memory read operation may be R, write operation may be W, whereas for IO read operation may be RI, just read from the IO device. Okay, write operation may be WI, write to the IO device. Like that there will be some slight differences in the command. Okay, with this command itself you can understand, okay, this is an IO read, this is an IO write, whereas this is a memory read, this is a memory write, whereas in memory mapped IO you cannot make such differentiation. Okay, so this is the difference between memory mapped IO and isolated IO, right? So all these we are discussing as a part of programmed IO. Okay, in programmed IO the it can be either programmed IO or interrupt driven IO. The concept of addressing the IO device. The concept of addressing the IO device is of two fashion. One is memory mapped IO, the other one is isolated IO. In case of memory mapped IO, there will be only one address bus which will be shared between the memory and the IO devices. Whereas in case of isolated IO, there will be a separate address bus, there will be a dedicated address bus for memory, and there will be another dedicated address bus to address the IO devices. Okay, I think it's clear. Fine. So here is a example like how memory mapped IO and isolated IO will work, and how it is and I mean and how it differs, right? So we discussed what in memory mapped IO the same address bus will be shared between the memory and the IO device, and IO operation will look just like a memory operation. You cannot differentiate. There are no special commands for IO operation. Only whatever the command that is being used by for the memory operation, the same command should be used for IO operation also. Because in memory also what you are doing, read and write. IO also what you are doing, read and write. So for memory read, what command you are using, same command used for IO operation also. Okay, to perform the read and write, right? Okay, so this particular code, what it does in the sense, actually it is used to read 1 byte from the keyboard. This particular code is used to read 1 byte from the keyboard. So this is the code using memory mapped IO. Let us see the code using memory mapped IO. If you observe the code using memory mapped IO, it will be similar to accessing a memory location, because in memory mapped IO the address bus is shared between the memory and the IO devices. So the instructions are similar as if you are accessing a memory location, but actually here in fact we are accessing the IO device. Are you getting? And this is the code from an isolated IO to read one byte or one word from the keyboard. Okay, but here if you see, the instructions will be quite different. By the instructions itself we can understand that this is an IO based instruction. This is not, here we are not, by seeing the instruction itself we can understand that here we are not accessing the memory, here we are accessing the IO device. But by seeing these instruction you cannot differentiate whether it is a memory operation or an IO operation. Okay, but let us see how it works. Right. So what we have understood, every device will have an address. Okay, keyboard also will have address, right? So keyboard has an address, right? Inside the keyboard there are two registers. One is the data register. So in keyboard, for example, user is typing something X. Okay, then the ASCII value of the X will first come into the data register before going into the IO modules, buffer or memory or wherever. Okay, first it will come into the data register. So this data register is present where? It is present inside the keyboard. So whatever user types, first it will go here. Okay, right? This data register is referred using the address 516. This address 516, it refers to the data register, input data register of the keyboard, right? Okay, this is the first point. So whenever I say 516, it means that data register or input data register of the keyboard. Okay. Next, inside the keyboard we also have a input status and keyboard input status and control register. Inside the keyboard we also have a keyboard input status and control register, and this register is referred using the address 517. Okay, this register also contains 8 bits. Okay, here let us try to understand. If this 0th bit is set, if this bit is 1, means it means that perform a read operation. It means you are giving a command. It means that as if a command is given to the keyboard to perform a read operation, then it means that keyboard will wait for the user to press a key. Whenever the user presses a key, that corresponding key will come to data register. If user press the key A, the ASCII value of A will come into data register. Okay, but that will happen only if this bit is set. Are you getting? If this bit is set and if user is pressing A, then the A will come here, right? If this bit is 0, now user is pressing A, nothing will come here. Okay, because if it is 0 means, it means in keyboard you can only perform read, you cannot perform write. If it is 0, it means that don't start the read operation, right? Okay, I think it's clear. So whenever the read operation is to be done, then this bit will be set to 1. Who will set this to 1? Whose job it is? It is the job of the job of the IO module. IO module, what it will do? It will set that bit to 1. Okay, maybe through some set of instructions. That is what we are going to discuss now. Okay, but somebody should set this 1 so that the whatever the user types, no, that can be read by the keyboard and it will go into the keyboard data register, right? Okay, fine. So if this bit is set, it means that perform a read operation, read one character from the user, right? Now see this, assume that this bit you are setting at time t0. Okay, now user should type a key, press a key, and the data should come to the data register. All these things will take some time, at least some milliseconds it will take, right? It won't take it will not happen just like that, right? So it will take some time, right? So once this bit is set, it means that the keyboard is ready to receive an input, right? Say now user presses a key, right? And user presses a key. So user presses the key A. So after some times, maybe after 10 milliseconds or 20 milliseconds, this A will come into the keyboard. I mean this keyboard data register A will come. Okay. Once the data is read from the user, then immediately this most significant bit should set, which means that the data is ready. Which means what? Data is ready. When this bit is set, it means perform a read operation. When this bit is set, it means data is ready. If this is 0, it means that keyboard is busy. It means user is typing something and keyboard is transferring the data to the data register. That is what is happening. Are you getting? So this understanding is required to understand this program, so that I'm explaining, right? So if the least significant bit is set, it means that perform a read operation. Once the read operation is successfully done, that particular character will come into the data register. Once the data register got that character, then this most significant bit will set, which means that data is ready. If data is ready, now the IO module can take the data and it can keep it in IO buffer. Are you getting? In the IO's buffer. Then from there it will go to memory. That is the way in which it works. Okay. Now let us see how this should be programmed using memory mapped IO and using isolated IO to read one particular character from the keyboard. That is what we are going to discuss. Okay. Fine. So first let us see for memory mapped IO. So the first instruction you see, load accumulator. Load accumulator. Okay, load accumulator with 1. It says that load the accumulator with the value 1. 1 means what? 0. So let us assume 8 bit. Simplicity, let us assume 8 bits. So all the 7 bits, 1, 2, 3, 4, 5, 6, all the 7 bits will be 0. The last bit should be 1. Okay, so this is accumulator. So accumulator, this is what now it contains 7 ones, 1, 2, 3, 4, 5, 7 ones and 7 zeros and last 1. Okay, load accumulator with 1. Store accumulator, see this, store accumulator to 517. What is 517? This is the catch here. What is 517? Address 517 refers to the keyboard status and control register. Address 516 refers to the keyboard data register. Okay, so store accumulator to 517, which means that store this content to 517. What accumulator contains? All zeros. So all these are zeros. 0, 0, 0, 0. Everything will be 0. The last bit alone is 1. If the last bit is 1, what does it mean? It means perform a read operation, start a read operation. So the moment accumulator is stored with 1, it means what? Initiate the keyboard read. Initiate the keyboard read. Okay. Now it will take some time. First user has to press a key. Say user is not pressing for 10 seconds. Then nothing will come into data register, right? If user is pressing at 15 seconds, after 15 seconds he is pressing A, then only A will come into the data register. Okay. So it is not that once this start is given, something will be available in the data register. No. It may be available or it may not be available. So you have to keep on check whether something is in the data register or not. How to do that? How to do that? Again, what we are doing, load accumulator with 517. Load accumulator with 517. Okay. Right? Load accumulator with 517. Why once again we are saying 517? See, once this A is returned to the memory, I mean in the data register successfully, what will happen? What will happen to accumulator, this most significant bit? It will become 1. Otherwise it will become 0. Right? Assume this A has not yet written. Assume this A is not yet written. Now if you load accumulator with 517, what is in 517? The same thing will come here. Right? Same thing will come here. Here what we are checking, branch if sign is equal to 0. Sign bit means the most significant bit. Most significant bit is always called a sign bit. So if sign is equal to 0, go to 202. Sign is 0 means what? If this bit is 0 means what? Busy. Keyboard is busy. Still it is reading. The read is not completed. That is the meaning. Still A has not come to the data register. That is the meaning. Right? Okay. So it means go to 202. What is 202? Once again load accumulator with 1. Once again store accumulator with 517. Once again set the read operation and keep on waiting. Keep on do this. Keep on doing this. Right? Say after some times this A is available in the keyboard data register. Once the A is available in the data register, this will become 1. This will become 1. Okay, if this becomes 1, then what we are doing? Again we are giving here what? Load accumulator. Are you following? First store accumulator with 1. Then store accumulator to 517. This 1 comes to 517 means perform read. Now user is given pressed A and A has come to data register. Now we are Once A came to data register, this most significant bit will be made to 1, because some data is available, that is ready, data is ready to read. Okay, so this bit will set, right? Now once again we are saying load accumulator. Okay, once again we are saying load accumulator from 517, load accumulator from 517, whatever the content of 517, that will be loaded into accumulator. Now what is the content? This most significant bit is not 0, now it is 1, now it is 1. Okay, so this location at present now we are having 1, so it means what? Data is available, right? So now you check if branch, if sign is equal to 0, is sign is 0? No, it's not 0. So then what will happen? Load accumulated from 516. What is 516? 516 is the data register. So this A will now come into accumulator. Are you getting? Now this address will be removed from accumulator. Whatever the data, what data we have read, that A will come into accumulator. Okay, so this is how a data is read from the keyboard using memory mapped IO, right? But here you can see only if I say that this 516 refers to data register of the keyboard and this 517 refers to the control register or status register of the keyboard, then only we can understand that it is performing some IO operation. The operation is connected with the keyboard. If this is not known, what is this 517, what is this 516, if all this is not known, then by seeing this instruction, can someone differentiate like whether it is an IO operation or a memory operation? No, you cannot differentiate, because it is just saying load accumulator, store accumulator, load accumulator. It means we think that it is some memory operation, but actually it is an IO operation. Okay, but it is a memory mapped IO, so you cannot differentiate, because in a memory mapped IO, a single bus is shared between the memory device and the IO devices. That is in nutshell. Okay, now let us see how the same task will be done in isolated IO. In isolated IO, see, the instruction itself is different. At first what we are doing, load IO, we are directly saying load IO. So this command itself says what? IO means load some IO device, and that IO device is referred as 5. So here 5 refers to keyboard. Here 5 refers to what? Keyboard. Okay, it means that initiate a keyboard read. This means load IO with 5 means, it means initiate a keyboard read operation. Then what we are doing, test IO. Test IO 5. Again 5 represents keyboard. Check whether the IO operation is completed or not. That is what test IO means. So then we check branch not ready. If the IO is not completed, then again go to 201. That is, keep on testing until the IO is not completed. You keep on test. Okay. So if it is completed, that is, if the IO is completed, then ready, then it will become ready. It is not, if it is not ready, go to 201. If it is ready, then this last instruction will execute, which means what? Load data byte. Okay, LN means load. LN means IO load. Okay, whereas this is memory load. So load the particular data byte from this particular device. 5 represents keyboard. Okay, so the difference between the two is, here from the instruction itself we can understand that this is a some operation connected with IO, because here itself the term IO is coming. Okay, load IO, test IO, with this itself we can differentiate, and there are different code too for different IO devices, right? Okay, so this is how we program memory mapped IO device and isolated IO devices, right? Okay, fine, let us stop with this. We'll continue the interrupt driven IO in the next class. Okay.